second goal on this part of part 2.2, this third day. How does the derivative apply to position, velocity, acceleration? Oh boy, physics. Well, this is not a physics class, this is a calculus class, but calculus relates to physics very, very well. I'm going to be worried about how the calculus works, not necessarily so much about how the physics works. We're going to give you some very, very basic physics. Those of you that are in physics are going to have a little bit of an advantage, but not much, because I'm going to be worried about the calculus part of it rather than the physics part of it. All right, so position, velocity, acceleration. Average velocity, instantaneous velocity. Average velocity. If I could give you the best example I can come up with, let's say today I'm going to leave here, I'm going to go home. I'm going to jump in my car. I'm going to be in my car for a period of time, and on that period of time, I'm going to drive home. On that trip home, I'm going to have an average velocity. How will I find it? I'll need to know how far I went relative to how long it took me. So change in position over change in time. Okay, change in position over change in time. Now what we're going to be talking about physics-wise is we're going to be talking about this general position function. And some of you guys, actually the people that are in physics can probably throw this out, and they're going to be, by heart, be able to tell me what's going on with meters, but we're also going to do some things with feet. So general position function, in calculus, a lot of times we like to use the letter S. Why? I don't know. But if we're doing this thing in feet, general position function's got something to do with gravity and how fast it was the object was being forced at the beginning and how high or low it was forced from. So this general position function, if we go through and we clean it up, negative 16t squared plus v naught t plus s naught. Well, what do those things mean? What's the v sub 0 or the v naught thing? Well, v naught is your initial velocity at time 0. V naught, initial velocity. And S naught, S sub 0, is your initial position. And again, what we're working on relative to the ground. So how high or low was this thing tossed from? So when I go to find this average velocity, I would simply need to know what was my position at the time I finished. Whoops, I don't want an equal sign there. Minus what was my position at the time I started, divided by what is my change in time. How much did the time change over the same period? So there's your position function. So again, to give you an idea what's going on, average velocity is my trip home. What was my velocity on my overall trip home? Okay. Instantaneous velocity then is a little bit different because my instantaneous velocity is at a specific time. And that specific time, oh, sorry, I forgot about down here on the bottom. I forgot if we were doing this exact same thing and we were doing it in meters like my physics people, I'm sure, have been well trained. Well, that would be negative 4.9 t squared plus v naught t. Let's make that look like a plus sign. Plus S naught, same V naught, same S naught. And the difference would be if we're measuring gravity using meters, we're going to have something to do with a negative or a 9.8 something or other. If we're doing it with feet, you're going to have something about a 32 in there someplace, feet per second. So instantaneous velocity then says this is going to be at a specific time. This is going to be S prime of t. Why is it S prime of t? If you think back to when we were doing all that derivative stuff, the derivative gives us the specific rate of change of a function at a specific time. Well, velocity is defined as change in position with respect to time. Well, if we're looking at a specific time, now we're going to need our derivative to help us figure that out. So instantaneous velocity, what's the best example of instantaneous velocity I can give you? How about the police radar gun? Let's say that today on my trip home that I'm going to find this average velocity for, there's a specific place in time where an officer feels the need to talk to me about how fast I was going. Going on the radar gun, that isn't going to be my average speed, or it probably won't be. It might be. but the idea is the average velocity I could figure out by knowing how far I went versus how long it took. The instantaneous velocity, I'll need the police radar gun to help me figure out because it's at one time. So instantaneous velocity. And the other thing that we have in here is acceleration. Well, my physics people would tell you that acceleration would be the rate of change of your velocity. If velocity is the rate of change of position, acceleration is the rate of change of velocity. Well, how do we find acceleration? That is the second derivative of your position function. How do you find second derivative? Second derivative, you take the derivative of the derivative. So whatever that is, some things that you might be getting used to then. Acceleration is either s double prime of t, or we would call it v of t, or v prime of t if we were playing around with it. So, all right, let's put this in practice. So we're dropping this ball from a height of 100 feet. When we say position function, we're using feet. We're dropping it so there's no initial velocity, so v naught is 0. This is your s naught, and again we're using feet, so my position function, s of t, negative 16t squared. There's no initial velocity, so we can leave that term out because it's going to be 0, plus my initial position, which is 100 feet. So there's my position function that would give me its height off the ground at whatever time I wanted to plug in there. My velocity function we'll either call v of t, or we'll call it s prime of t. Well, s prime of t, take the derivative of that blue function. So negative 32t plus 0. So there's my position function. Give me the position at any time. Velocity function, give me velocity at any time. All I have to do is come up with what the time is. All right, average velocity. Questions A and B. Average velocity and instantaneous velocity. Average velocity. Okay, so are we talking about at a specific time or over a period of time? We're talking about over a period of time. So we're looking at the change in position over your change in time. So change in position, we'd be looking at s of 2 minus s of 1 divided by 2 minus 1 second. So it took 1 second to make this change. Where did it change from? Well, I need to know what its height was at time 2. S of 2, let's come up there to that position function again. S of 2, 2 squared would be 4 times negative 16 would be negative 64 plus 136 feet. S of 1, do the same thing. 1 squared is 1 times negative 16 is negative 16 plus 100 is 84 feet. So take those numbers and plug them in. So we've got 36 minus 84 in the numerator and a 1 in the denominator, negative 48 feet per second. Why is it feet per second? Because the position is changing in feet and the time is changing in seconds, negative 48 feet per second. Does the negative make sense? Yes, because that velocity is causing the position to get smaller. It's falling, so the position is getting smaller. So there's average velocity. What about just plain old ordinary velocity at 2 seconds? Well, now we're talking about at a specific time, so we're looking at v of 2 or s prime of 2. Whoops, sorry, let's put a 2 in there instead of a t. Or s prime of 2. Well, s prime of 2, find your derivative. We already did. It was negative 32t. Now we're using the red function up there. So negative 32 times 2 would be negative 64 feet per second. Why is that? Well, what that means is if we had a radar gun on this ball that was being dropped and we clocked it at exactly 2 seconds after it was dropped, it'd be traveling at negative 64 feet per second. When does the ball hit the ground? Well, the ball will hit the ground. What will its position be? Well, its position will be equal to 0 when it hits the ground. So we're going to take our s of t function, set it equal to 0. Well, let's see if we go to solve. So 100 is equal to 16t squared. Let's divide by 16. We're going to have t would be the square root of 100 over 16 with a plus or minus on it. Square root of 100 would be 10. Square root of 16 would be 4. Plus and minus, the minus won't make any sense because we're talking about a time. So the time that this happens would be at either 5 halves or 2.5 seconds after it was dropped. Part D, what is the velocity of the ball as it hits the ground? Well, is that over a period of time? No. as it hits the ground. So we're talking about the velocity at a specific time. What is that specific time? V of, I don't know, S prime of, I don't know, however you want to relate it. Well, that time is this 2.5 seconds. So take your 2.5 seconds, plug it in your velocity function, and we're going to end up with an instantaneous velocity of -80 feet.